In this lesson, we're going to look at how to work with vectors in 2 dimensions. So a lot of the time in physics when we're learning a new topic, especially one to do with vectors like motion or forces, we start by looking at problems in 1 dimension. For example, in our study of motion, you probably would have started by looking at objects that moved in 1 dimension, which means along a straight line. So maybe a car that sped up and then came to a stop, or a ball that was thrown up in the air and then came back down. And once you've mastered that, there's an opportunity often to move on to looking at that same topic, but in 2 dimensions. So for example, a ball that instead of going straight up and straight down is thrown at an angle and kind of goes along a curved path, moving in the up-down dimension and the left-right dimension at the same time. That would be an example of a 2-dimensional problem with vectors. So far in this course, we've been looking at 1-dimensional problems, which means when we come across a vector, we can plug it into a formula by representing it as a number that can be positive or negative. For example, in like a northeast-southwest problem, things that are going north, we would call that positive. Things that are going south, we'd call that negative. Or an east-west problem, things going east, we'd call positive. Things going west, we would call negative. But if we start to deal in 2 dimensions at the same time, like in this example down here, where I'm given a velocity of 32 meters per second with a direction of 10 degrees north of west, it's not so clear how I would write the direction of this vector. The north part makes me think I'd want to write this as a positive number. But the west part makes me want to think maybe I'd use a negative number. This is kind of between north and west, so is there something between positive and negative I can use? And we see pretty quickly that it's tricky finding a way that I could type this number into a calculator, say. So, as a reminder, our compass directions, when we're writing them on a page, we generally write it as north towards the top of the page, south towards the bottom. East and west are right and left. Writing this down as just a simple number that's positive or negative is really hard to do. We can't. But what I could do is I could write it down as an arrow. So 10 degrees north of west looks something like that. So writing this down as a single number is difficult, but writing it down as an arrow is fairly straightforward. So what this means for our problem solving is that when we're working in 2D, rather than plugging numbers into our equations, we're going to have to plug in arrows. And let's jump into an example of how maybe we might do this. So, after accelerating at 4 meters per second squared south for 3 seconds, a hovercraft full of eels ends up traveling at 30 meters per second east. What velocity did it start with? Now, at first glance, this reads a lot like a typical universal accelerated motion 1D kinematics problem. I'm given an acceleration, I'm given a time, I'm given a final velocity, I'm asked for an initial velocity. So let's start by setting up this problem much the way we'd set up a 1D kinematics problem with universal accelerated motion. Okay, so I know the acceleration. This is metric base units, so my units are all good on that. I'll write it down as 4 south, magnitude and direction. My time is 3 seconds. Again, that's metric base units, so my units are all good there. And for final velocity, I've got meters per second, which is metric base units. So that's all good. I can write this as 30 east. I'm looking for VI, and I don't know what the displacement is. The next thing I would probably do, again, I haven't even really acknowledged the fact that this is a 2D problem yet. I'm just solving it as if it's a 1D problem. The next thing I would do is I'd pick a formula. And turns out a formula that has VI but not D is this guy. VF equals VI plus AT. Then since I'm looking for VI, I'm going to rearrange the formula to isolate VI. And I get VI equals VF minus AT. And the next thing I would do is I would start plugging things in. Here's the first time where we need to recognize this is a 2D problem and do things a little differently than we would have in a 1D problem. In a 1D problem, I would probably just say, oh, 30 east, east is positive, so I'd write that as a positive 30, plug it in here. For south, south is traditionally negative, so I'd write that as negative 4, plug that in here. But because this problem has sort of the east-west dimension and the north-south dimension, that would be confusing. If I type that into my calculator, if I sees a negative now, doesn't know if I mean west or south. So I can't reduce these to just positive and negative numbers. I need to keep these direction words in here. That's going to be crucial. So I'm still substituting things in, but I'm keeping those direction words. So VF is 30 east. A is 4 south. And T is 3. So I'll make a note here because this is the first thing we've done that's a bit different. Is that we can't just use plus and minus for direction. Okay, now we can again sort of forget temporarily we're working in the two-dimensional world and think, what would I do in a 1D problem here? Well, I need to subtract something and I need to multiply something. My math knowledge of bed mass tells me I need to do this multiplication before I can do this subtraction. What's a bit different here is, how do I do this multiplication? This is a vector, 4 south, and this is a scalar, 3. How do I multiply a vector by a scalar? Now, generally, I find with students, if I ask them that question generally, and I say, how would you multiply a vector by a scalar? It's pretty hard for people to kind of come up with a solid explanation or guess as to how to do that. But if I simply use this example and say, what do you think 4 south times 3 is? People generally say, oh, I think that would be 12 south. And indeed it would. If I have an arrow of length 4 heading south and I multiply it by 3, it basically gets 3 times as long, but stays the same direction. So 4 south times 3 is 12 south. And so that's the next note I want to write down here. We've used it right in this step here. To multiply a vector by a scalar, we multiply the magnitude and keep the direction the same. Okay, so now, in order to find VI, I've got 30 east, 12 south, two vectors, and I'm subtracting them. Again, this is an operation that's a bit different from what we're used to. Now, you have lots of experience, most likely, adding vectors together. You know, when you add vectors, they can go in any order, they have to go head to tail, and the resultant goes from start to finish. But this isn't adding vectors, this is subtracting. So what I like to think of here to convince students about how to add vectors, or how to subtract vectors, is I think, well, it's kind of the same as with numbers. If you had a friend who was great at adding numbers, they could add any numbers you gave them, but they didn't know how to do subtraction. What you might tell them is, oh, subtraction is just adding the opposite, or adding the negative. So, for example, 5 minus 2 is the same as 5 plus negative 2. To subtract 2, I basically add negative 2. Vectors work exactly the same way. So to subtract this vector, I actually can add the opposite. Question is, what's the opposite of 12 south? Well, as you might expect, I basically just flip the direction. We can think of this as putting a negative in front of it. And the opposite of 12 south is 12 north. So, by substituting in, doing a little bit of simple math with vectors, I've determined that to get the answer to my problem, all I have to do is take these two vectors and add them together. So let's just write this note about subtracting vectors, and then we'll get to adding these two. Okay, so 30 east plus 12 north, that should give me my answer. I just got to add these, which means I got to put them head to tail. .30 east, .12 north, and the resultant is going to go from start to finish. Okay, so VI is basically the result of adding these two things together. So this resultant here is my VI. That's what I'm looking for. Because this is a vector, it has to have magnitude and direction, meaning I'm going to find the length of this and also the way it's headed. It's not going straight north, it's not going straight east, it's going somewhere between the two. So I'm going to have to use an angle to accurately define this direction. And one thing you might remember is when we're defining the direction of a vector, we always use an angle at its tail. So there is an angle for that touches this vector up here, but that's by the head of the vector. We want to use a vector at the tail, an angle at the tail, when defining the direction of a vector. So I'm going to put theta down here, and we'll write that as a note to ourselves. Always define a vector's direction from its tail. Always define a vector's direction from its tail. Okay, so I need to find the magnitude and direction of this guy. Well, to find its magnitude, you may recognize this triangle as a right triangle. Because this was east and this was north, there's 90 degrees between them. So I'm basically just trying to find the hypotenuse in a right angled triangle. And for that, I can use Pythagoras. Rearranging for c, which is my hypotenuse, I get the square root of 12 squared plus 30 squared, which gives me 32.311. I'll use 5 sig figs here because I'm in the middle of a problem, and I'll kind of round it to 3 at the end. To find the direction of this vector, theta, I can use SOHCAHTOA. Again, because this is a right angled triangle, regular sine, cosine, tangent worked well. So if I want to find this angle, I can use information from the opposite side and the adjacent side to help me with that. So that makes me think that using tan would be useful. So let's go for it. So tan is opposite over adjacent, or 12 over 30. Then what I want to do is I want to isolate theta to get theta all by itself. Problem is theta is being tanned, so I want to get rid of that. I want to undo it. How do I undo a tan? Well, I undo a tan by using an inverse tan. So in front of this tan, I'm going to throw an inverse tan. Now, number 1 rule in algebra tells me I'm allowed to do that as long as I do the same thing to the other side. Here, this inverse tan and the regular tan cancel each other out. So I have theta equals inverse tan 12 over 30. Or theta equals 21.801 degrees. So let's recap here. I had this problem where I was looking for an initial velocity. I figured out that if I used this formula, I could isolate for initial velocity, and everything else in the formula I would know. I plugged everything else into the formula, but because some things were in the east-west dimension and some things were in the north-south dimension, I didn't just use plus and minus for the directions, I kept these direction words. Then I took care of some simple math, multiplying a vector by a scalar, changing subtraction to addition, and I ended up with an expression that told me if I could just add these two vectors together, I would get my answer. I then added them by drawing them out head to tail and finding the answer, or the resultant, by using Pythagoras for its magnitude and SOHCAHTOA for its direction. So this magnitude and direction that I ended up getting here should be the answer to my question. So the initial velocity of the hovercraft is 32.3 meters per second with a direction of 21.8 degrees north of east. Again, this notation here, north of east, means if you want to get to this vector, start by pointing east, the second direction I've given you, and then go 21.8 degrees north of it. So north being that way, 21.8 degrees north from east, and that gets me to my vector. Now, one thing that was nice about this problem that won't always be the case is when we drew out this triangle to add the vectors together and find the resultant, we had this nice right angle in there. Right angles are great because they let us use Pythagoras, they let us use sine, cosine, tangent, but we don't always have right angles. So let's next look at a problem where we don't have a right angle. All right. An object moves 12 meters in a direction 30 degrees north of east, and then 7 meters in a direction 15 degrees west of north. What is its total displacement? We're going to solve this problem twice, once using a components method and once using sine law and cosine law. But first we'll do components. So what I'm going to do here is start by drawing a nice big diagram for this guy. Let's start down here. So I'm going to go approximately, let's see, 30 degrees feels like maybe that. And so there's my .30 degrees north of east. And then I'm going to add to that 7 meters at a direction 15 degrees west of north. So here's north, and you go 15 degrees west of it. And this guy is a length of 7. Okay. And adding those two vectors together should give me the resultant, or the total displacement, which I'll do in red. Remember, the resultant from a vector addition problem goes from start to finish. Okay, and I'll just add in this 15 degrees here. So here we have a triangle that does not have a right angle in it. Not there, not there, not there. Which means we can't use Pythagoras, we can't use SOHCAHTOA. So what we're going to do is we're going to start by taking all of the vectors that are being added together, and we're going to split them into components. And the idea with components is this. You can replace any vector with two vectors that add to make it. This actually, again, works with numbers too. So if you really didn't like the number 5 for some reason, Every time you saw a math problem with the number 5 in it, you could erase the 5 and replace it with 2 plus 3 or 4 plus 1. And then keep doing the math problem and you get the exact same answer. Works the same with vectors. So for example, I really don't like this vector because it's kind of, it's at a weird angle. I like things that are going straight north-south because then I can just say north is positive, south is negative. Or straight east-west. So then I can just say east is positive, west is negative. I don't like having to deal with angles. So I'm going to see if I can replace this vector with two vectors where I don't have to deal with these angles. And indeed, I can. So this plus this gives me this. These two vectors add to make this one. In other words, these are the components of this vector. One x component and one y component. Just a matter of finding out what those are. So a little bit of, since I know this hypotenuse is 12, I know this angle is 30, a little bit of trigonometry, SOHCAHTOA, can tell me that this side is going to be 12 times the cosine of 30 degrees, which is 10.392. And I can do the same for this side. This component is going to have a magnitude of 12 sine 30, which is going to be 6 right on the button. I'm going to do the same with this vector here. Again, I don't like this. It's going at this awkward angle. I'd rather not have to deal with angles, so I'm going to replace it with two vectors I like more. One purely in the y direction, and one purely in the x direction. This vector in the y direction is going to have a magnitude of 7 times cosine of 15 degrees, or 6.7615. And this vector here is going to have a magnitude of 7 sine 15 degrees, or 1.8117. Okay, and we'll just put a little reminder up here because we're dealing with northeast, southwest in this problem. There's our little compass reminding us which directions are which. And we can even write a reminder that north and east we consider to be positive directions, and south and west we consider to be negative. So how does this component stuff let me add these vectors? Well, instead of adding these vectors, I can now ignore them and I can work purely with their components, and I can just add their components. And the great thing about these components is that because they are at 90 degrees to each other, and these ones are too, the x and y components don't affect each other in any way. They are totally independent, which means I can add the x components together without thinking about the y components. And I can add the y components together without thinking about the x components. So let's do that. Looking at just the x components, I have 10.392, and because I'm only looking at the x direction here, I can use positive for east and negative for west. So this is going east, so it's a positive 10.392. And then I have a 1.8117. It's going west, so I'm going to use a negative for that. And that gives me the resultant of the x components is positive 8.5803. Now we can look at the y components. I've got two y components here and here. They're both going north, so they're both going to be positive. So I can just add those together. I've got positive 6.0000, and positive 6.7615. That gives me positive 12.7615. So what I found here is by adding the x components, I found the resultant of the x components. And by adding the y components, I found the resultant of the y components. But let's look back at our graph, or our diagram. The resultant of these y components, for example, was this plus this, so it went from here to here. If I take that same line and I draw it over here, we see that not only is this the resultant of the y components, it's also the y component of my resultant. And similarly, this resultant of my x components, this guy minus this little bit, just gives me what's left over here, which is the x component of my resultant. I'm trying to make these components slightly dashed. Okay. So this resulted of my x components, 8.5803, goes over here. And this resultant of my y components, 12.7615, goes over here. So I still need to find my overall resultant, but that's going to be a little bit more straightforward now, because I have now a right-angled triangle. And this is kind of the trick with this components method, is I started with this triangle here, right in the middle, that I did not like because it did not have a 90-degree angle in it anywhere. And I've kind of reduced it, or I've gone around it by looking at this triangle, and this triangle, and this triangle. So instead of looking at one triangle that didn't have 90-degree angle, I've looked at three triangles, all that do have 90-degree angles. And this is kind of the essence of the component method, is it allows us to do more work, three triangles instead of one, but with simpler math, 90-degree triangles instead of one that's not. So let's do our final step. I've got a right-angled triangle here, and I want to combine these two components to find the resultant. I can find the magnitude using Pythagoras and the direction using SOHCAHTOA. So I get 15.4 as the magnitude of my resultant. And then let's go over here and do the direction using SOHCAHTOA. I'm going to use, again, we always define a vector's direction from its tail. So I'm going to pick an angle down here to define the direction of my resultant. And I'm going to pick this one. This angle seems nice and clean. There's a little more garbage sort of going on down over here. And I should be able to find this because it's one of the angles in my right angled triangle. So I can use SOHCAHTOA to find it. I know the opposite side and the adjacent side, so I'll use tan. And that gives me theta is equal to 33.9 degrees. So, I have found the magnitude and the direction of my resultant. I've answered this problem using the component method. So my final answer is 15.4 meters with a direction of 33.9 degrees. And so this angle here is 33.9. I'll fill that in. And I'll even put my 15.4 in too. So this angle is telling me that to get to my vector, I need to start at north and then go 33.9 degrees this way, or east of north. So 33.9 degrees east of north. Okay. So that's an example of when you come across a 2D vector problem where you have a triangle with no right angles in it, how you can still solve the problem by breaking every force or every vector into its components and then looking at the components separately in the x and y directions. And like I said, in essence, we're basically, instead of solving one triangle with no right angles in it, we solve 3 triangles, all that have right angles. So we're doing more math, but it's simpler math. Now I'm going to show you another way to do this, where rather than doing more simpler math, we do less, more complicated math. Let's solve the exact same problem, see if we can get the exact same answer, but this time we're going to use sine law and cosine law. Okay, so let's start by drawing our problem out one more time. That'd be like 45 degrees, so 30 degrees is maybe like here. Sounds good. Okay, so 15 degrees, 30 degrees, 12, and 7. I'm trying to add those two together, and I'm trying to get the resultant, which goes from start to finish. Nothing new here. I've basically just drawn out the exact same diagram I had in the previous question. But instead of running away from this triangle because it doesn't have a 90-degree angle in it, we're going to just approach it head on. So let's try and find the magnitude and direction of this guy. Basically what I have here is a triangle where I know these two sides, and I'm trying to find this one. And I've got some angle information here. None of those angles are inside the triangle, but I can probably use that information nonetheless. So generally what I find, when you know two sides of a triangle and you're trying to find the third one, and you don't have a 90-degree angle anywhere, to find the magnitude, it can be pretty useful to use cosine law. So cosine law says c squared equals a squared plus b squared minus 2ab cosine of c. Now here's one really important thing to remember about the cosine law. People often think that c has to be the longest side of the triangle. I think because they're used to Pythagorean theorem, where c does happen to be the longest side of the triangle, because c has to be opposite the 90-degree angle. But when we use cosine law, we can use it for triangles that don't have a 90-degree angle. So we can't say C has to be opposite the 90-degree angle when there likely isn't a 90-degree angle. All we have to have is that C is opposite whatever angle we're calling big C. And since we can pick big C to be whatever angle we want, little c can be any side we want. So let's make a note of that. C can be any side you want. Choosing the side you're looking for works well. Okay, so let's just go in on this triangle here and label my sides and angles A, B, and C. I'm going to make C the side I'm looking for. The reason that works well is because then this equation is already rearranged to have C isolated. If the side I'm looking for is B, then I got to somehow isolate B, and that's going to be annoying because it appears in two places, and here it's squared. So if you're looking for a side, make that side C. So here's C, and then A and B I can pick however I want. I'll pick this guy to be A, and I'll pick this guy to be B. Now I have to label my angles so that they're opposite the corresponding letter. So angle big B is opposite side little b. Angle big C is opposite side little c. And angle big A is opposite side little a. So to solve for C, I'm going to need to know side A, 12, side B, 7. There's A and B again, and I'm going to need to know angle C. Ugh. Don't know that, but maybe I can figure it out. Here's one tip that I find becomes really useful in 2D vector problems. And it is looking at a triangle and looking for the letter Z, or the pattern of the letter Z. And I kind of see one right here. There's the letter Z. I think this is sometimes called the rule of alternate interior angles. I call it the Z rule. And it basically goes like this. If you have a Z pattern where you've got two parallel lines and then another line that crosses both of them, the two angles that are made, these two angles in your Z letter, have to be the same. So if this guy's 30 degrees, that guy's 30 degrees as well. The Z rule. Now, up here, I've got some other information. I know that between this dotted line and this dotted line is 90 degrees, because I made this one horizontal, and this one was vertical. And this little notch here is 15, so that means the leftover part from here to here is going to be 90 minus 15, which happens to be 75 degrees. So angle C, which goes from here to here, incorporates this 75 and this 30, so that's going to be a total of 105 degrees. All right, so I can start plugging stuff in to sine law. So C squared equals 12 squared plus 7 squared minus 2 times 12 times 7 times cosine of 105 degrees. I plug all that in and then take the square root to isolate C, and I should get C equals 15.378. Okay, so I didn't have to create any extra triangles. I've just been working with the one triangle I was given, and I found this side directly by using the cosine law. Next, let's find the direction, the way this arrow is pointing, by using the sine law. Now remember, we always define a vector's direction from its tail. So I'm going to pick an angle down by the tail of this vector for the direction. Might as well pick angle B, since that's right in our triangle and it's touching the tail of the vector. So the sine law says if you take the sine of any angle and divide it by the length of the opposite side, the number you get will be the same regardless of which pair you picked. Whether you picked B and B, or C and C, or A and A, you'll always get the same number, dividing the sine of the angle by the opposite side. So, since I'm looking for angle B, let's use my B pair in sine law. So sine of B over B equals, and then let's pick up, because I already have something I don't know, let's pick things I do know from now on. So I've got A and A, I know that length, I don't know that angle. Let's do C and C, since I know those. So the sine of big C divided by little c. Okay. Again, big B is the thing I don't know, but little b is 7. This will be sine of angle C, which is 105. And side C, I just found is 15.378. So this tells me that the sine of B is going to be 0.43969, and angle, therefore angle B, if I inverse sine that, is going to be 26.1 degrees. 26.1 degrees, and C is 15.4. Now hold on. I got an angle here, my direction of 26.1 degrees. When I did it the previous way, I got 33.9. Well, there's a couple of things going on here. It just turns out I'm not quite done yet. So when I'm defining the angle of a vector, I want to compare it to one of my standard compass directions, north, east, south, or west. Angle B compares my vector to this blue vector, which is not north, east, south, or west. So what I should probably do is compare it all the way, not just to this blue vector, but down to this dotted line. That is heading in the east direction. So the angle between my vector and this east direction is going to be 26.1 plus 30, or 56.1. So my answer is 15.4 meters. And then that angle here is 56.1 north of east. Right? Here's east. To get to my resultant vector, I'm going to go 56.1 degrees north of it. But wait, this still isn't the same as the angle we got up here, 33.9. And it turns out, whenever you define the direction of a vector instead of a northeast, southwest situation, there's always sort of two options for how to do it. This vector is between north and east. So I could compare it to north by using this angle here, or I could compare it to east by using this angle here. In the previous solution to this problem, we compared the vector to north and got 33.9. But down here, for whatever reason, we chose to compare it to east and got 56.1. Those are both totally legitimate ways to do this, and they're both considered 100% right. It's worth just checking that those two numbers we get should add up to 90 degrees, since the difference between north and east is 90 degrees. And if you check, 56.1 and 33.9 do indeed add to exactly 90. I'll write that as a note here. This is our final answer. And let's just note that this direction is the same as 33.9 degrees east of north. Okay, so two solutions to the same problem. One, where we used components to take some vectors we didn't like, a triangle we didn't like because it didn't have a right angle, and break those vectors into components, x components and y components, so that I created several small right-angled triangles. And then I solved all those triangles. I used trigonometry, sine, cosine, tangent, and Pythagoras to get rid of the hypotenuses and find these legs. And then I used them again up here to combine these legs or these components to find the hypotenuse to get this resultant. Lots of simple math with simple triangles. And then there's approach number 2, where I said, let's just deal with the original triangle. Let's not create 3 new ones. But because it's a more complicated triangle, it has no right angles, my math's going to be a little more complicated. Instead of using SOHCAHTOA, Pythagoras, I'm going to have to use sine law and cosine law, and a little bit of geometry to find some of these angles. Both approaches, however, got me to the exact same answer.